Hi, I'm Stefan Bökelmann, the organizer and host of the emBO++, the next level conference for embedded system developers. In this talk, you will see how to implement your own instructions in the LLVM toolchain. The talk was given by Tabea Röthemeyer at the emBO 2021, and thanks to Zega, you can watch this video for free.
Hello, everybody, and welcome to my talk, Implementation of Customized Classes in LLVM for RISC-V Custom Hardware, which is my talk for this year's emBO. Who am I? I am Tabea Roethemeyer, and I'm currently working as an engineer at Auto Intern, where I'm mostly doing data acquisition and analysis of the data that our sensors tend to send to us. I've also worked on compiler editions for the past month, and this is what I'm going to talk about today. What exactly do I want to talk about? Well, first of all, I want to introduce you to the problem that led to compiler modifications. I want to have a brief look at both hardware and compilation infrastructure, show you the results of benchmarks and why they're interesting, and at the end, wrap up all the results of my talk. So let's start. First of all, what was my problem? So the group that I worked with tried to find a solution against the attack speculative execution tends to offer. We just don't want these attacks and find countermeasures. There is several research going on, but none of it seems to be suitable for all corner cases. So the idea is to totally get rid of speculative execution. But as most of you probably know, speculative execution comes with a lot of performance benefits that we will lose. So we got a new problem. We need to solve the performance because, well, running code that has low performance is not really desirable. So they thought of another approach to get performance without having to enable speculative execution again. The idea was we're using the means of code analysis to reduce the number of times the processor is not sure which instruction is next in the pipeline. And this is done by putting the code in a block-like structure of certainly executed codes. So the task of the code analysis is to find out if one instruction is executed, how many of the following will be executed certainly as well, put that into a block. And then the processor's task is mainly to find the next basic block that is executed. So we get performance not as great as speculative execution, perhaps, but at least good enough to accept the solution. The part of it that I worked on attacked loops because lots of code is structured in loops. And if you analyze how often a loop is executed, then you can tell the processor just this number, so you don't have to check the loop condition during runtime. This requires hardware modifications. So the telling the processor how the blocks are structured comes with new instructions that tell how large one of these blocks is. I use this as the exemplary story for my talk. If you're interested in more details, there's a paper which is called the basic blocker approach, which is about redesigning instruction set architectures to eliminate speculative execution attacks. You can find it on arXiv if you want to. So what exactly is hardware from a programmer's point of view? Because to be honest, I'm not a hardware developer's person per se. So the processor, in my point of view, is the one that executes code. It only understands zeros and ones, which is a format that I certainly do not speak. So I rely on code generation tools that, turn my code into something that a processor understands. These tools, however, rely on the mostly on the instruction set architecture. This is kind of the abstraction of a processor. It contains, for example, the list of instructions a processor implements, but without having too many details. So as a software programmer, it's okay to read this manual because you're not getting too many details of the processor's implementation. It's quite suitable. and mainly the interface for software and hardware developers to talk about what a processor should be able to do or not to do, and what they can work with later on. The instruction set architecture that we used for our problem was RISC-V. RISC-V is a license-free and open source instruction set architecture that is around for, well, quite some time for now. It has a huge community. And there are also several implementations, tools. You can get different processors that actually implement a subset of RISC-V in one form or the other, which are either, well, ASIC designs, but you can also get hardware descriptions that you can put on FPGAs or also soft cores. We use the VEX RISC-V just in case you're looking for something for your projects. This is great because open source projects mostly allow to modify them or add something as you need for your application. It's easy to simulate how the processor works without actually having to manufacture one, because these obviously comes with lots of cost, especially because you normally need to iterate over your processor over and over again as you make mistakes during the process. Plus, you don't have to start from scratch. That's always great because you get your goals faster. What are the instructions that I want to add? As I've already told you, I want to enhance loop performance. And this, the hardware concept that we focused on were hardware loop counter. So normally, after every loop execution, the loop condition is checked. This is, well, if you do not have speculative execution, this is not that interesting because you rely on evaluating this condition, which leads to stalls because you're not sure whether the loop is executed again or if you continue with the other code. An analysis method that helps to determine how often a loop is executed is scalar evolution analysis. This mainly says that this is an analysis method that has a look at how variables evaluates structurally per loop execution. So this can also be done with the loop condition variable. And by evaluating how it is changed throughout the loop, it can derive how often the loop is executed. And even if this is a deterministic behavior or if this depends on code segments that are without this, not in the scope of the loop. If the loop seems to be deterministic in the number of executions, we can let another unit, the hardware loop counter unit, take care of the execution. So you basically tell it how often the loop is executed and what code belongs to the loop, and then it will just execute this code. So that's the idea of hardware loop counter. This results in changes to the code because, as I already told, we don't need this conditional branching. But we do need to initialize the counter and mark the scope of the loop. And this has to be done with additional instructions. So let's say that we have a processor that already has this new instructions implemented, which are these, I will cover this later. The more interesting part as a programmer is how do we actually create code that profits from these new instructions? Ideally, without relying on writing machine code. Before we actually dive into the compilation process, I wanted to show you what exactly we would love the code to be turned into. So on the left, you see a very basic for loop. We could discuss whether this is an interesting one or just for the sake of the argument. However, on the right, you see what the instructions executed on a processor would look like. So you see that there is an lcount instruction, which is the one that initializes the loop counter. And you see this BB instruction. This encodes how many instructions belong to the block and if it is the start or end of a loop. So this one contains 2 instructions, and it is the start and end block of loop count set 1, which is this one. This one is code after the loop. So now we want to see how we get this transformation to be done automatically. In general, compilation is done to translate hardware-independent code, high-level language code, into something that is processor-dependent, machine language format, because this is what makes the code executable on some hardware target. So we now have to choose a compiler. We're going for LLVM and have a look at how compilation is done here. So in LLVM, we have 3 major steps that are taken during the compilation process. First of all, we have the high-level translation that translates from a language like C++ into LLVM intermediate representation. LLVM stands for low-level virtual machine, and this kind of indicates the concept that the intermediate representation is like a virtual machine's language, kind of. On this intermediate representation, all the code analysis, possible refactoring, and optimization is done. These are arranged in passes, so every optimization is one pass that runs through all the code and does whatever analysis it is implemented to do. These passes operate as independently as possible, so you can rearrange them, use their results as you please. Well, there are some rules that apply, but yeah, that's the main idea. Once you're done optimizing the intermediate representation code, you can get into the target code generation. And here the instruction selection for the target actually happens. So this is the task that we are interested in, because this replaces all the intermediate representation instruction with the ones actually executed. And if we're adding a new one, we possibly have to tackle this part of code generation. So we have to modify the backend because this contains the instruction information. Targets in LLVM are described in the backend, and their structure is the same for all of them. So there are some rules how to describe what kind of storage they have, what instructions they have, when to use them, stuff like that. And they all have a similar, because of the similar structure, you can rely on some properties to be set that you can use in the intermediate representation if you feel like it. Now we're actually describing the new instruction by modifying the code that describes the target in the compiler. This is important because if you do so, you have to recompile your compiler to actually let these effects take effect later on. This sounds rather theoretic, and I actually took some time to get the concept, so I wanted to show you some code. On the bottom, you can see how the instructions were intended to look like. So we got 32-bit instructions. This is the basic block instruction that encodes how many instructions belong to the block if it is the start or end of one of the loop counters. And there's a sequential flag that indicates if the next basic block is also executed sequentially, because there might be more than instructions than fit coded in here. And then we got the alcon instruction. This one tells us, I'm having to link, sorry. So here we got the alcon instruction. This one encodes how often the loop is going to be executed, and it possibly can encode a register where the value can be found, and this is stored in another special function register, basically. This is how the instruction definition looks like in LLVM. You define some properties for every instruction, and then you define how many bits are belonging to each of these sets, and they all got names. So this is how instructions are described in LLVM. Now that we have the instruction on the processor and also implemented it in the backend, we actually can insert it. The questions to ask to insert them the right way is first, what code structures actually profit from the new instruction? So this is basically why did you begin all this effort in the first place? If you have a concept of what code profits, you need to find markers that identify the structures that you can look for in the code. If your identification is too loose or too strict, you will either not get the full profit from your new instruction, or you might put code into, or you might transform code that is not suitable to be transformed, and your results will never be correct. And then when you know how to identify the structures, you need to find a way where to actually insert them. Maybe you got restrictions that you have to place your instruction before or after a certain other one. In my case, the loop counter has to be initialized before setting the first basic block that belongs to the loop. How did I do this in my example? First of all, I wanted to profit from infrastructure that was available in LLVM, because this not only makes my personal work easier, but also if more people work on the same problem, you probably get a better result than if you only do this on your own. Hardware loop counters are a concept that is not implemented on all processors, but some do have such features. So instruction set architectures by ARM or Hexagon, or also PowerPC, have hardware loop-like instructions. So some of the analysis was also was already put in a generic hardware loop path, and I used it and customized it because there was a possibility to do so. I adapted the criteria for selecting loops, and then I had to mark the loops that are interesting, or the analysis marked the loops. This was done by intrinsics, which is a construct in LLVM that you can search for and that contains information about your system. It looks a little bit like a weird mixture of functions and variables, kind of. Then, if I have the intrinsics that are inserted during during the optimization phase and on the intermediate representation, we actually get to insert our new instructions in the backend. So there, I searched for the intrinsic. I initialized the loop counter with the correct value and put this before the very loop code. And then I had to delete all the artifacts that were created, because LLVM obviously doesn't know that I used hardware loop counters. So I had to delete all the branching stuff related to my loop. In general, of course, this applies to all hardware concepts. You use them to enhance your processor's performance, and you probably are not the first person to implement them. You're probably the first person to solve this very problem on this very processor with this concept, but you're not probably not the first person to use a concept in general. So it's interesting to find the details in which your implementation differs, but also the smallest common denominator, so that you can put some general analysis that you can modify for your very own needs. I think in LLVM this is done quite beautifully, because you can rely on the code optimization phase to do such analysis result, and it interacts with the backend by calling certain functions to make sure that well, yeah, the results are correct. These functions are mostly called is profitable functions, something like that, and it worked pretty well. So now we finished phase 2, so we could compile code that actually uses this new feature. Hopefully, there is a process of some trial and error to actually get your compiler to compile, and you probably do some first testing to see whether your instructions get inserted and stuff. But well, we finished phase 2, and we're starting phase 3, which is answering the question, was it actually worth the effort? How do you test the impact of your new instruction? You will probably use benchmarks. So you compile your code with 2 compiler versions, with and without a feature. So you got just one very small parameter change.
Wir sind hier in einem kleineren Grossraumbüro.
Bei der Leica habe ich die Freiheit, dass ich, wenn ich anfange und wenn ich höre mit dem Arbeiten, eigentlich selber einteilen kann.
Overall, how I will do it, it's just up to me and they give me a lot of freedom.
Für mich ist die Faszination, mit anderen Leuten einen kreativen Moment zu generieren.
Great colleagues, great environment basically.
It's really nice here and I don't have any issues living here.
Am meisten schätze ich in den Leica Geosystems, dass wir ein sehr junges Team sind, sowie dass ich auch meine Arbeitszeit in einem gewissen Raum selber bestimmen kann.
And I could merge my life hobby with my office job.
Das Besondere an der Leica Geosystem ist sicher die Kultur und die Dynamik, die es gibt in dem Team. Es ist jeden Tag ein bisschen anders.
We have good organization which will help you to get used to the company in the first couple of months especially.
Das ist sehr interessant und ja, macht mir Spaß.
So the results are as comparable as possible. You execute the code, both versions, on, in our case, the simulated core, and then you compare the results. This is actually where it comes in quite handy that RISC-V processors can be simulated and that there are hardware descriptions of them, because then you can easily adapt the hardware description if you're able to write hardware description languages in a correct way, which I find still fascinating that people are able to do so. One note that I had to learn the hard way: make sure you choose code that you're sure you could potentially profit. So if you don't, your results might be different from what you expect it to be. Because I like graphs, this probably isn't the prettiest one, but still, it felt great to have some results after all the effort. Here you can see different versions of compilers, so there are more features tested. The most interesting one is the for each benchmark is the last one, which is loop counters enabled. And then you can see that you want them to be lower than the blue one, which is just no speculation at all, which is the worst case scenario that we want to avoid. And as we are always better than this is quite a cool thing. As you can see, the green ones are if you include the basic blocker concept, which already gives you huge performance benefits. This one actually indicates that there might be some bugs to be fixed in this thing. So yeah, these are the results that indicate mostly that the hardware loops seem to increase the performance. So it was worth the effort. And to put it in a nutshell, first of all, you have to add the instruction description to the backend, if you're lucky and your backend is already described, but RISC-V obviously is. Then you have to add analysis to find the suitable parts of code in the optimization pipeline. This analysis hopefully marks the suitable parts in the intermediate representation, so you can use them in the backend. On the backend, you have to add a pass that inserts the new instructions, replaces the marked ones. And then you have to compile your compiler and profit from the compiled compiler and maybe evaluate your results with benchmarks. My very own conclusion to this talk and the work I put into it, I think LLVM is awesome. There's so many resources and talks that you can rely on that help you, so many nice people, totally worth having a look at it if you haven't done already. Also, hardware concepts are quite fascinating because hardware is always designed to solve a problem the most efficient way. And well, solving problems can mostly be done in a generic way, and using the correct hardware concept is, to me, feels kind of like using the correct algorithm. So being able to extend your processor's instruction set architecture by 1 or 2 hardware concepts is really, really cool. Additionally, I was really surprised how much infrastructure surrounds the RISC-V projects. So you can simulate your processor and test it and adapt it and stuff like that. It was really cool. To conclude, if you have any questions left, I would be happy to answer them or discuss them afterwards. You can also feel free to approach me on Twitter or LinkedIn if you feel like it. Thank you for watching. So I got 2 questions. First one is, do you think that there will be a whole lot of people now implementing their own instructions in RISC-V? Where do you think this will go in the near future, and does it have a practical benefit? Or was this basically intellectual gymnastics? Well, I think it was kind of intellectual gymnastics because, to be honest, speculative execution is still really powerful in this particular case. However, there are use cases where you might want to get rid of it. So I think this might be used in the near future. Overall, well, this was quite some work. So even though it's less work than it would have been years ago, it's still lots of work. So I don't think people will just go around and, well, implement their own processors and stuff. But it's a great tool to keep in mind, I think. Yeah. Another question is it a question? RISC-V is a nice choice as it can be played with and then put into FPGA without need for creating custom silicon. Yeah, that's what I thought too. So you just can actually test your processor if you want to. It's really, really cool. So another comment was speculative execution is one thing. A side channel can also abuse other mechanics. It's an interesting research topic on how to balance speed and security nowadays. Maybe Epic Rebirth is on the horizon. I don't know. I think I've seen a lot of research going on. It's an interesting field. Yeah. Paul asked, do you think that having a lot of different instruction set architecture dialects is a problem, or are there easy ways to handle this? I think this depends on how you're using your instruction set architecture. If this is a very custom one to your problem, you will probably be the only one using it, and you will not modify an instruction set architecture in such a way that it's not recognizable anymore. So handling this probably is easy. If you're generating like sub-instruction set architectures, would be interesting to see if there's things like substandards or something to it. If there are hardware concepts that widely used that people do not want to take the effort to implement them themselves, might be the case. So Odin asked, if people go crazy with customized silicon and compilers, how many different compilers will Godbolt need to integrate? Actually, that's quite cool. I considered finding out how to integrate my very own compiler into Godbolt because I read on Twitter that Matt implemented this option somehow, which is really cool because Godbolt is just an awesome tool. So the answer would be just one Godbolt, but you have to get your compiler into your very own Godbolt version, I think. Paul commented, the RISC-V already has a long list of letters after them to show what parts are supported. Yeah, that's true. Actually, it's kind of hard to keep track of the letters, but them having letters is quite a nice way to show that they differ. I think that's one approach to go. Maybe there will be a better one in the future. I don't know. I'm not sure if the next comments are related, to be honest. Yeah, so if there are not any other questions that are currently pending, thanks again for all the questions and listening to my talk, and maybe we can discuss later on. Yeah, or see you on the rooftop and stuff. It was a pleasure to give this talk. To be honest, this was my very first one. It was so much fun.
If you found this video informative, make sure to subscribe our channel. Click the thumbs up if you liked it, or leave us a comment on what we could improve. If you are looking for a job in the embedded industry, or you've got one to offer, drop us a mail to jobs@embo.io. That's jobs@embo.io. And we'll make sure that you match up. My name is Stefan Bückelmann, and as long as you keep watching, we'll keep covering the internals of the embedded industry.